Welcome back to the online video lectures of this computer vision course. In the last video lecture, in the last Zoom session, we started discussing about the scale invariant feature transform, which is crisply referred to as SIFT, right? And in that class, we also discussed that there are two key aspects that the SIFT tries to address, which are otherwise not addressed in the classical Harris corner detector. What are those 2 points? Scale invariance. The name itself has these two features. So first two is scale invariance. If you have a feature, could be a key point when you look at it at a different scale. It might not be a key point at a selected scale, but it could be a key point at a different scale. And not each some of those points might be very good key points, but not necessarily all looked at the same scale. But when you look at them at different scales, you could one of them which otherwise is not a key point could become a very good candidate for key point. That's one aspect. And in respect to the scale invariance, another point is you might be having a zoomed out version and a zoomed in version of a given image. So repeatability is also badly gets affected when the same image is there but at a different scale version, and if you are still using the same scale as the original one while searching for a key point. And let's say in the Harris corner detector, if you are using your second order moment matrix to look at whether that's a key point or not, then it would be missing, and thereby in the second image, since it is missing, the repeatability would come down, right? What was the second point we were discussing? Rotational invariance, right? See, in one image you might be having this, but when you have it rotated, you still want to get them mapped. Of course, you are partly or in fact right that it is a kind of somewhat relevant to the descriptor, but you could see it as an intermediate step between detection and description also. Okay, you start describing it after you normalize it with respect to a dominant orientation in your image, such that you would get rid of rotational invariance. So we left or we finished the last class by saying that, asking you to ponder about how you could bring rotational invariance into scale invariant feature transform. So this image would tell you also another thing. You could see this whole computer vision textbook is now buried in basmati rice, and I don't know what it is. Okay. Yeah, and this book is rotated. Now the goal now is you should be able to still say that, let's say this face is what corresponds to, hope you could still see the face here. Okay, and this guy's face corresponds to this, so that rotational invariance is. And finally, once you find out the mapping of the key point, they should get matched, and you should say that, well, this book is this one but with so and so rotation. That's the basic idea of scale invariant feature transform. Let us at this point look at scale invariant feature transform at a very high level. Like, it has a detector part, and you are not enforced to use this detector part. If you want to use descriptor independently, you could still use the descriptor. That's what in fact many people does. They use for descriptor Harris corner detector that we discussed. And just now, as we discussed, you could see orientation assignment as an intermediate step. It's up to you. Could put it in description, but that's a better way to look at the algorithm. So you would assign a you need to figure out which is a dominant orientation in the image. You orient it in that direction, you rotate that key point patch in that direction, and then this becomes your new north. Okay, hope you understand what I when I say north. Assume that this is your dominant orientation. Let me, I think I have an image here. Yeah, so this is a better image. Suppose that this is your point at which you are looking at, and in the surrounding patch this is what you have. So essentially what I want, or what we want to do is, you could see here a lot of edges are in this direction, so in a way this is your dominant direction. You make it, now you rotate a image along your dominant, not the image, in fact the patch around your pixel in that direction. and then you describe that point. Okay, so the next question that comes from here as a consequence is that how do you figure out which is a dominant orientation in a given patch? That's the question now that you need to come up with an answer. So by looking at it, you can say that there is a strong edge in this direction, there is an edge in this direction, there is an edge in this direction. Okay, so if you look at, you could say that a dominant edge is there in this direction, right? That you could say, that's easy to say here, right? But given an image, how do you figure out which is a dominant orientation? You are given an image, so for example a similar thing here. So if you look at it, this is having one intensity and then there is a change of intensity, so this is your dominant orientation. Now you are going to first, as a first step, for that point you first align it along its dominant orientation, then only you do whatever you want. Okay, now the question is, how do you, given a patch in your image, how do you figure out what is the dominant orientation? That's the question you need to answer me.
Identify some gradients,
Hmm.
like, or just the edges within an image, and then we can sum up the gradients, and whichever resultant gradient is pointing to, that could be.
Um, yeah, can you be more? You are, so basically you need to work on gradients, right? That's for sure. Correct. And now, how do you figure out? I'll give you this patch. Okay. How do you figure out which is the dominant orientation? So what you would like to do is you want to sum up all that, take an average of all of them, right? That's what you wanted to do.
No, sir. I was thinking more in the direction of a vector sum. So
Hmm.
we can take the vector sum of all the gradients, and
Right.
whichever direction it points to, that direction could be the. Uh,
Okay, not at all a bad beginning. That's in fact good. So can you come see? Can you can you come up with some more better approximation or a simplification of that? Instead of taking anyway, at the end of the day, you are summing up everything. But of course, as you rightly said, on the vector space, not just like the values. It's both. Since there is both magnitude as well as the direction, so you want to take that also into account and come up with a simplified version to figure out. See, I want to roughly see, the moment you see this image, you would say roughly, well, the you won't like to look at every you see, this is also in a way an approximation which is a dominant direction, rough, that's a rough approximation to more or less align things. So can you think of anything simpler version?
So we can find tan inverse of gx by gy for every pixel, and then we can find which angle is most prominent, which
Hmm.
angle is present in most of the pixels.
So how do you I am fine, I understand till 10, you are going to find out in a way the orientation for each pixel, right? And after that, how do you find out which is dominant? That's the question. So what it does is it creates 36 bins. See, there are overall 360 degrees, so each 10 degrees it is considering as one bin. Okay, now what it does is it creates a histogram of all pixels, so gradients of orientations of those pixels. So it goes to each pixel in that patch, you compute the orientation, you put it in the bin that it falls into, the closest bin that it falls into. Let's say if you are considering 5 degrees here, so 0 to 10 would be one bin here, right? That's what you keep under this bin. Anything from 0 to 10 you would keep in the first bin, then next bin could be, and then you may eventually assign it to 5 degrees, let's say. That's what you would say as the dominant one. So then 10 to 20, 20 to 30 and so on. Okay, or 20 to 29 perhaps. Okay, in that way you do it. You look into the orientations and then you look at which is that bin. Okay, this is where, see, in a, at the end of the day you want a representative statistics. So if for such things, you know, already histogram would help you quite a lot. It's more like a statistically that would tell you which is more dominant. And it, in addition to considering the orientation, it also weights that with the based on the magnitude of your gradient. See, there could be a very almost uniform region with slight even then you are not worried about which orientation it is showing, because that's after all a uniform region. So it is indeed makes sense to weight the vote that you are you are doing here in between 0 to 360 degrees based on the orientation. If you add to that, if you it makes sense to weight it based on the magnitude of your gradient, right? And then you pick that which is having maximum value in the histogram, let's say this one. So maybe you could assign it an orientation of 15 degrees, and then you that's your new north. That's what the terminology Professor Aaron Bobick uses. Then you are rotating it in that direction, so that would become now, suppose this would become, now you rotate the whole thing. So next time also when other image comes, you do the same thing, and then you do the rest of the processing here. Okay, so this is also referred to as canonical orientation, that which you computed and you are coming up. And of course, the implementation from scratch, the SIFT scale invariant feature transform is, and then making it work is not at all a trivial job. Okay, it has a lot of parameters. If you simply do that, it won't be enough. Then there is a smoothing that has been done on this histogram, in fact, and then this voting to the neighborhood of that, and then from there are a lot of other details as well. But our job here is we will get an intuition and we will skip the details, okay, for the sake of getting a good overview picture, so that we will not get stuck in those details. This is what we do. Hope this is clear to everyone. Is there any question here? And again, he does a very extensive experiments on lots of images, where he in fact introduced I think around 5% noise, and saw how many are at varying noises. He rotated the actual images, and then it did a detailed study and figured out that taking 36 bins each with 10 is computationally efficient as well as reasonably accurate. That's how he arrived at this empirical number of 36 bins, if I am not wrong. Okay, again, this is very close to the way you thought about. Any questions on this?
Sir, a question on the um, like how where do we perform this algorithm? Uh, is it after detecting the corners from the Harris corner detector? Do we do that?
Yes, that's right. You just look at here, you finish your key point localization here, and after that you are getting it. See, because this orientation is not going to impact whether it is a key point or not. It is actually, you could think of it as a pre-processing step to later, when you get another key point which might be a rotated version of this, to find a matching between them, this rotation is required. That's a very good question. So you do this, as you could notice here. First comes detection, then comes orientation assignment, and then aligning it in that particular orientation, then followed by description. See, sometimes what could happen is another, as I said, he nicely says the devil is in the detail for SIFT algorithm. That's what Professor Aaron Bobick nicely puts it. Again, what could happen is sometimes you might, the dominant one, you might find out some other peak which is very close to it. Let's say um, this might be another peak you might be getting here, this area also in this manner. Okay, this is very close. And again, this is a kind of approximation. You are taking bins, and because of that, you will not be pretty sure whether orienting everything, or this is probably is not a you are at least still close when you are orienting it. Assume that somewhere at a very far away angle, okay, you are getting something like this. So what to do then? How confident you are that maybe one is, let's say, zero point 0.4 and another is 0.37? Okay, how confident you are that this is your dominant direction? Well, definitely not very confident. So what he does is he considers one key point as in fact two key points, and one key point you are getting by putting it in this orientation, and another, ignore about this what I kept there, another by putting that in this orientation. So one. Now instead of one, you branched out into two. Now you treat them as two key points, find out a matching but with a different angle. That's what this statement says. Okay, is that clear? So now you could see a key point is now characterized by its location x comma y, and it's a key point at a particular orientation, not at a particular scale, not at every scale. So you need to know what is that scale value, and then comes orientation. So now a key point is not just x y, it is a vector of four features: x, y, scale, and orientation. Is that clear? And now if you look at the same point when it is having very close values of dominant orientations, then your orientation 1 is one key point, orientation 2 is another key point. Hope that point is clear to you, right? Again, this is just yeah, so I purposefully skipped for now discussing about the detection, because you already have some idea about that, because we discussed Harris corner detector on top of its scale invariant Harris corner detector. So I thought it is important to grab your initial attention to the things that have been introduced newly into the SIFT. So we will come back, we will discuss still the detector, but perhaps in the next lecture. Okay, so for example, you have now a smoothed image L, or you could call it as difference of Gaussians if you are representing it with the D. This is how you would be computing the magnitude and the gradient of the pixel there. Okay, you could see here you are computing a derivative in the x direction. Yeah, something very close to that. The square of this difference is taken there, that would give you direction in x square. It's like square root of gradient in the x direction square plus gradient in the y direction square. That's what would give you the magnitude. A very similar thing has been done here. Okay, maybe some constant of 1 by 2 is missing, but doesn't really matter, because anyway you are doing the same thing for everything. So then you are looking at the relative magnitudes to take a call there. So it doesn't really matter even if you are doing central difference scheme for computing gradient x and gradient y and dropping that 1 by 2 there. Okay, similar thing. These calculations are exactly in similar lines to what we did while doing the gradient computation classes. Hmm. So then, yeah, you have 36 bins are used, and you do then on top of it, you do a spatial filtering here, because your pixel central pixel is somewhere in the middle, and then to the orientations that are coming from the central pixel you want to give a more weight. So one, let's say, spatial Gaussian filter with variance of 1.5 times the scale of the key point is also another important thing you need to apply, because each one is at a this is why he nicely says the devil is in the detail. If you blindly apply for every key point 1.5, it is not going to work out, because that's a key point. Each one is a key point. It could be a key point at different scales. That also you need to keep it in mind while you are applying a Gaussian smoothing on top of it. Okay, and then assume that this is what you got at the end. Okay, can you tell me what is the length signifying there, and what is the direction signifying there? So the length is the magnitude that you have seen here. Okay, and theta is telling you the orientation. That too after after this are what you are getting up. You apply that at every point here. Okay, then you are getting certain things there, and on top of it now you do the quantization. Of course, before quantization, you apply a Gaussian smoothing there, and then this is what you are getting. And if one peak, if another peak is within 80% of the maximum peak that you have, then you take in fact two orientations you consider, and that serves apparently as two key points. Okay, clear so far? If it is clear, we will move on to the now. You have brought a new north direction, you aligned your patch in that for a given key point. Now you still need to describe this point. So if you have no questions for orientation, alignment, and bringing it into the dominant direction, if that is clear to you, I'll move on to now SIFT descriptor. Any
Um,
questions so far? Yes.
uh, Sir, the scale of the key point, is that the same again from the Harris corner detector algorithm?
Right. The scale invariant Harris corner detector we discussed, right? It is in very similar lines. We will anyway in the next class we are going to discuss it in very detail. But it is in very similar lines. That is assured. Now we are into a very important step of which I would say, or many would say, as the important contribution of scale invariant, the most important contribution of scale invariant feature transform. That's the descriptor. Okay. Now before telling you what he does, I would like to hear from you. This is, for example, a patch that you have aligned with the new north, or which the new north for you is the dominant direction. Okay, so this is your, let's say, your key point. By the way, another thing he does is he normalizes all these patches to one scale, particular scale, because see, every time you know what is the size of the patches, you can always expand or contract, or in another words resample it such that they are all at same scale. Okay, so that is also done, by the way. Okay, and then you, if you're in your direction of the dominant one has been rotated such that your dominant direction is in the north direction, so that's how it has been rotated. Now I want to describe this point so that later I could compare it with something which is there in the other image. What do you think is the way that you could encode or embed, okay, this particular point? So how do you describe, what do you think are the ways to describe this patch so that you could later compare it with the patch coming from other image for a given key point? Now for the time being, assume that the scale has been sorted out, rotation has been sorted out. Okay, all are at same scale, and the orientation has been already taken care. Now you want to describe this point. How do you describe it?
That patch is there now divided into some blocks,
Hmm,
and you are computed the histogram for each one.
very good.
We can write that for each block as
Hmm,
store somewhere to
hmm.
compare to the other patch of other image.
Okay, but let me, maybe I would ask you specific questions. See, one way I could think of is you anyway, rotation has been taken care, scale has been taken care. What if I look at the patch for the other key points coming there and compute the square of differences there? What is the problem with that if I do that? Is there any problem? So in other words, my key point here is just the simple, my descriptor is simply this 2D array. Okay, so maybe I would create a 1D array from that, right, by concatenating all rows here. Say for example, I'm considering here 16 by 16 patch here. Okay, so I have a vector of size 256 here. Now I simply subtract it from the other, and then take L2 norm basically. So for each so what I will do here, so xi minus yi whole square, something like that, where my I varies from one. If I start my length from 1, it would be 1 to 256. Okay, this is one descriptor is x, another is y, something like that. If I compute, and suppose if they are identical and same patches, it could be 0 if intensities are same. But where is this descriptor going to fail? By the way, is that clear what I told you? What is it I'm computing and how I'm describing a given point? I'm simply, this is a 2D array of 16 by 16. I would concatenate all rows. So I have a single vector of length 256. This I do for each point in coming from one image, and I do the same for the points coming from the other image. Now I'm going to compute this metric of another one. I subtract the respect to take the difference of the respective elements there, corresponding elements, square them just to get rid of the differences, positive or negative, sum them up. If the difference is minimum, then I would say this belongs to the same point. Okay, that then I would say that patch which is resulting in a minimum value of this is the corresponding key points. So what is the problem with this kind of metric computation? So if you are adding intensities, are this is getting added up in a nonlinear fashion. Okay, there is no way. Had it been a simple additive noise, okay, if you call that as noise, or noise is perhaps not the right word, or the intensity yi is a times xi, there is no problem. Okay, and similarly yi is equal to xi times some n naught. Okay, no problem. But if you have yi equal to, let's say, a times xi plus some well, if it is varying in a nonlinear fashion, okay, so maybe xi square. So in that region, depending on the location, if it is varying, so then there is a problem. Then n naught, this is not going to, ncc is going to fail. Okay, so is there any other way than using intensities and computing the normalized cross correlation? What is the other way to describe it? Because intensities have, because of illumination changes, could end up in such problems. So what is the other way to represent a given point other than intensities?
Gradients.
That's all. You could use gradients. And then if you are using gradients, so one way you could think of is, you still have this vector of 256 size, where instead of intensities you have gradients there. Okay, but the problem is, if you are using each individual gradients, you are very conservative, and you are very strict there, because when there is a rotation, or while you are computing this dominant direction and all these things, because of the noise also, there could be certain instances where some portion of your image might be, or within that portion, this is a very strict condition. So then there is a trade-off between what? Trade-off between using every intensity versus using a simple histogram for the entire patch. So what did that trade-off being, what you do is, you are going to, I'll make small jumps here, the whole image patch, you are going to divide it into again small patches here, and for each patch, okay, you take gradients, or histogram in other words. But this histogram, it need not be, again he has done a very extensive study on how many orientations are reasonably good enough, because you don't want to have it too many orientations, because at the end you want to encode it. Okay, if you are taking every orientation of 1 degree and doing it, that itself for a given block would give you a length of 360, which is quite big. So he was looking at which is reasonably good enough, and arrived at the number that having 8 orientations for each patch are giving him reasonably good results. Okay. And what the other thing that he has done is, he is dividing it into 4 blocks, 4 by 4 blocks, 1 2 3 4 here, and 1 2 3 4 here. And within each block you again have here 1 2 3 4, 1 2 3 4. So each block has 16 pixels. Okay, so what is the whole patch size now?
256.
That's right, 256 are there. So you are constructing histograms for 4 by 4 patch, that means for 16 pixels each. And in the histogram you are using north, south, east, west, northeast, okay, southeast, southwest, and northwest. So kind of 45 degrees you are taking angles, these bins. So for example, this could be minus 22.5 to plus 22.5. You keep it in east and you do the binning there. So at the end of the day here, you have a vector of 8 points, you are putting them in a specific order there. So how big is your feature vector. That's what I'm trying to work out with you. So here, for example, you need 8 values here. And how many such patches are there? How many such blocks are there now? How many blocks are there? Such blocks, one block here. If I consider this as one block, how many blocks are there?
16.
16 blocks are there. So 16 into 8, how much is that? 16 into 8?
128.
128. So now you are representing a given key point with a vector of size 128, where you could, for example, think of it as you will concatenate this at the end of this, then at the end of that you will be concatenating this row, and at the end of that you will be concatenating this row. Because of concatenating in the specific fashion and then comparing, notice here you are kind of looking, making sure that this patch, as long as is, instead of looking at a pixel level gradient mapping, you are looking at a small block level mapping of gradients. Okay, because see, everything is a kind of an approximation. The rotation is earlier within, it could be plus or minus 5 degrees to what you get there, right? So you should give it some breathing space there later to get it mapped. So that's why here you are again considering it in steps of 45 degrees and a patch of 16 degrees, because you should account for small misalignments also while you are doing it, because of so many approximations you are doing. So because of that, you are looking at in a patches of 16 pixels 4 by 4 region. And then of course this blockwise mapping you are doing for a 4 by 4 blocks. Is that clear? This is a very, very important contribution of scale invariant feature transform. Is those numbers, is that so normal? Anyway, as I said, first you are rotating the window is done. Scale the windows, all bring it to one common size is done. Okay, that is done. Now, given a patch, you computed these. This illustration is just showing you on a 2 by 2, but original one is 4 by 4. I think this is the one. But just take for a quick illustration. These are again, most of the slides are from Professor Aaron Bobbick's lectures. So you are dividing it, for example, this one 4 by 4 to this, you have a kind of a histogram here. Okay, again in very similar lines to what has been done to compute the dominant orientation. These are weighted by the magnitude of your gradient, and on top of it there will be a Gaussian smoothing applied. On top of it there is a smoothing applied, some kind of smoothing applied within the histograms. There is some smoothing applied. So let's not go into those minute details, let's not get lost there, but rather the ignoring those details, what has been done, why it has been done, and why it works, that should be clear. And of course those numbers should be clear to you. Okay, anyway, the kind of interpolation to compute that and other things are there. I don't want to get into those details, but just maybe I will talk about this, where let's say he has rotated one image by a 50 degrees, and he had added a noise of 4%. Again, it is very comprehensive, you just look at this paper once. And then he is looking at correct nearest descriptor. Okay, that's what he is computing there. And he tried it with, by using just 4 orientations, by just putting the north, south, east, west. Okay, quantization. So in a way each one is 90 degrees. He tried with 18 orientations, he tried with 16 orientations. And the patch sizes are here: 4 by 4 patch, 3 by 3 patch, 2 by 2. See here, I told you here you have it 4 by 4, but for arriving that also he has done very exhaustive comprehensive evaluations, and he has seen that the percentage of correct ones are here, there is a saturation here. So beyond 4, even if you are considering 5 by 5 patches and so on, it is giving you, notice that this would in fact then increase your length of your feature vector, so which you would ideally would like to have a with a small size. So if you still remember the first class of desirable properties of key points, it should be very compact, right? So then it is almost saturating here. That's what you could see. And then well, this strong line is for 16 orientations. In fact, it is, so this is what would happen when you are very conservative. So that's in fact is not with the, when there is a noise and rotation, it's not helping you much. And same is the case here. These are all empirical studies done on a very large data sets. Okay, and then the similar thing is happening with 16 orientations. There is was a problem, 4 orientations. Okay, and then this was something which then he figured out that having 8 orientations would be good. So that's how he arrived at these empirical numbers. This is how you encode it. Okay, as I said, again, there are few more details here. One of them is, for example, in a given image, there is a, because of an illumination variance, there could be one peak coming there in just one, in the whole image here, which you are considering. Maybe in this patch, because of the illumination variance, this might be dominating your whole vector, right? So that's why he, again, to address that, he does normalize it to unit vector to deal with this. And after that, even if you normalize, that magnitude would be so large compared to the others, so it will not help you to actually tune it based on this is only the driving force, then the whole thing goes array, could go chaotically. So what he does then is, this 128 size vector, he puts a threshold of 0.2 to be the maximum value. Anything, vector value, okay, this vector value is coming as this value here. Okay, that value more than 0.2, he clips it to 0.2. Again, when you are clipping it, the magnitude of that is no more one unit vector. So again, here not renormalizes it to unit vector. These are all again the details. Anyway, you don't have to worry, as I said, too much about it. But that's, but still you should be knowing why something of that nature is required. That's what is done for the descriptor part. Okay, so that's what is about the SIFT descriptor. We are done now with the orientation. So I come back to the overview slide here. Orientation assignment we are done with. Key point descriptor is something we are done already with. And then these are the two things, the detector part, which I would discuss in the next class. Okay, since we can afford 5 more minutes of time at least, if you have any questions here, doubts here, please let me know. If something is not clear.
Yes, sir.
Yes.
Sir, actually, when we identify a key point and
Hmm.
when we normalize it with respect to rotation,
Hmm.
how exactly do we take the 16 cross 16 pixel uh, patch? Because when it is rotated, we can't take a square patch, right?
Hmm. Very good.
Uh,
That's
but
where,
we have 16 cross
yeah,
16 pixels here, so
correct, correct. So while you are rotating, again, you resample your image after rotation, and you do that with a 16 by 16. That's how you have it. It's not like you take it. That's why here, even in our overview, I'll come back to that slide here. You do the orientation assignment and then you rotate that patch in that direction, and then you resample it to a grid of 16 by 16 there. Using trilinear interpolation, he uses it. So basically, then you to figure out what a value it should have, you would look at the values here, 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 around all these points, and figure out what would be the new value here after the rotation part. So you have to do interpolation for each patch or key point, by after applying this rotation, and then give a grid of 4 by 4 or whatever there. Is that clear?
sir, so we have to do a little additional computation to get
Yes,
the
that's right.
rotated patch.
So applying rotation and bringing that alignment would require an additional computation of resampling the image, such that you have now a regular grid around this pixel.
So for the flat region,
Hmm.
this will not work.
Right. See, first of all, also make a note here. you are first finding out the key point, okay, a set of key points only that represent the image, and it is only for those key points you are doing this orientation alignment and then description. So it is the job of your key point detector that it will not give you a flat region. Just that our sequence, in our sequence I did not go through the one, but as I said, you imagine here a Harris corner detector, okay, scale invariant Harris corner detector. It is giving you the key points that are what have been given for orientation assignment. You align them properly, you scale them appropriately, and only those points you are going to describe. So by the time it comes here, you should not be having any uniform regions. Then your, it's not the descriptor that failed because it is expected to fail. It is the detector that failed there.
Sir, can you repeat what is the purpose of giving weights to the bins of the histogram?
Okay. So you mean Y2 weighted by the magnitude? That's your question, right?
Yes, sir.
See, if I give you this image, any image, hopefully I would come to some image. Okay, see here. Let's say you would figure out, see, by just knowing the orientation, it doesn't tell you whether it's really a strong edge or not. Here, for example, there is something here. This also will have a orientation here, and maybe this also will have a orientation here. But while alignment, you would prefer if you have at another image taken from a different viewpoint, that alignment happens based on those points which have very strong edges, right?
Okay, sir.
Because
So we are
noise,
doing this.
yeah.
So we
So
are doing this for the entire image.
no. You are doing it for the patch around it. For example, here the patch size is 16 by 16.
Okay, okay.
While doing it, so one thing is you are doing it at the time of orientation alignment also you are doing, later describing the key point also you are doing, because knowing just orientation is not good enough. You should know really in that orientation, do you have a strong edge or not? That's even more important question. So if it is a very feeble edge, that might have been contributed even by noise, so that should not impact your descriptor much. So you are looking at whether that's a strong edge or not. So that's why you are
Okay.
taking weighting based on the edge strength. Okay. And of course, if you are looking at a pixel centered, okay, center pixel is the key point for you. So anything that's, as you move away from it, the weight given to that, even now computing the same thing weighted by your edge strength, in addition to that, that contribution should also go less. So if this is going to be your key point, then that also, those weights, another Gaussian smoothing weighting is also there. Is that answering
This
your
this
question?
this descriptor means we are considering rotation and scale invariance. Means when it has like a squeezing, means uh, the projection
Mm.
itself is actually squeeze the image and
No, no,
uh,
no. A description is, see, that's why, let me come back here. See, if this orientation assignment should take care of rotation of the whole patch there. Okay, that has been taken care there. And after that, this is at a very large scale you are doing it, then within that there could be some misalignments later when you are you are going to compare it with the different key points that are coming from other images and see whether this has any mapping there. That is when again there could be slight so you expect them to be almost in a similar orientation because you align them with respect to the dominant orientation, but still you could allow some flexibility there for various reasons. So that's why again you are using a histogram. Okay, if you are not using histogram, the possibilities are also, your length is becoming also quite large from the experiments, as long as you are taking bins of 45 degrees and then trying to see if these two rotationally normalized vectors to say so are matching or not.
Yes, sir.
Is
Actually, like I had a little bit of doubt when you're talking about that 4x4x8
right. Let me go
blocks.
there.
I want to know exactly like how did we get that 4x4 from that patch of 16x16? Like I had a little bit of doubt.
Okay. So yeah. So basically you are now given a point, and the scale also has been normalized. So you would consider a size of 16 by 16 here.
16 by 16 is a patch around that particular key
Right.
point
Correct.
in the
Correct.
image.
Right.
Okay.
Right. This is your 16 and this is your 16.
16. Okay.
And this is basically you take, then you divide it further into 4 by 4 here.
Okay.
Okay. And then you, for this each block, now how many blocks you have? You have 16 blocks now.
We have 16 blocks. Yes.
Right. For each block, now you have 8 values here. This is a histogram.
Okay. So each block basically we are finding the localized gradient for every pixel.
Right.
Then we'll put it in a histogram format.
Right.
That
Correct.
will like classify into 8 different directions. Whichever
That's
direction is
that's right.
okay.
So that's why you have then 4 by 4 into 8. That's 128 length of 120, vector of length 128 you have.
Okay, so sir, just one more question. Is there any specific reason why we are choosing like 4x4? Like,
Yeah.
what difference would it make if we chose something like I don't know 8x, I don't know, so 2x4, like
Yeah. Yeah. This is
split
the
it
thing.
into lesser number of blocks?
Yeah. See, just that you expect that rotation has been done and there is no end to this whole process. But he has done very thorough experimentation where just to reduce, this is another, otherwise 3D you should be doing. So he has taken as
Okay.
an assumption here, this is a 4 by 4 thing. That's all. That's an
Okay,
assumption.
so that is an assumption we are
Right.
taking, and then based on that we are finding for different number of orientations,
Right. So he
basically.
has taken
And
assumption that
yes,
the window
okay.
is a square window, and then he experimented with the 1x1, 2x2, 3x3, 4x4, and so on. And you
Okay.
ideally want a with a small window, you get maximum, because that is what is deciding your the length of your vector. Okay, which you want to
Vector,
be minimum.
yes.
So with 4 by 4, he is getting reasonably good results overall. And in the tomorrow's class we will discuss about SIFT detector part. Okay. Yeah. Mm, thanks. See you tomorrow.